Okay, good morning, everyone. Welcome back. So hopefully you finished all of your housekeeping, refactoring, cleaning everything up. Hopefully you have a little bit of a clearer picture of where everything goes in your code base. And we will continue pushing on today in assignment 6 by adding neurons, the penultimate piece that's needed for your evolutionary robotics experiments. In the neurons assignment, you're going to get close, but not quite, to closing the sense, think, act cycle. So we've got our robot with its sensors. We've got our robot with its motors. The motors send commands to the joints. The joints apply forces to the objects, which causes the robot's relative orientation and position in its environment, changes its relationship with its environment, and assuming it has enough and the right kinds of sensors, at the next time step of the simulation, it's going to sense the change in its relative orientation and position to the environment. Okay, so we're getting one step closer to closing the sense, think, act loop. In assignment 6, you're going to be adding 3 different types of neurons, which we've talked about already. Sensor neurons, which are going to receive values from the sensors. Motor neurons, which are going to send values to the motors. In assignment 4 from last week, you were just sending values directly to the motors. Now we're going to be taking the values from the motor neurons and sending them to the motors. And you're going to be adding some hidden neurons, which, as the name implies, are hidden from direct influence of the outside world. Assignment 7 next week, we will finally close the sense, think, act loop by adding some synapses that connect the sensor neurons to the hidden neurons, some synapses that connect the hidden neurons to the motor neurons. And if you want, you can add recurrent synapses that connect the hidden neurons to themselves, back to the sensor neurons, however you like. It doesn't really matter in assignment 7, as long as we have some synapses that transform sensor values into motor values. So in 2 weeks' time or less, you will have this. Once you do, in assignments 8, 9, and 10, you will be wrapping this whole system in 3 increasingly powerful evolutionary search methods, evolving your robot to do something of interest to you. All good? Any questions about last week's assignment, this week's assignment, assignments in general? All good? Okay. So back to our discussion about the history of evolutionary robotics, admittedly a relatively recent history. We almost finished lecture 9 last time, minimal cognition. We were looking at 4 of the building blocks of cognition. We got through 3 of them last time. What were they? Ironically, if you don't remember, you're failing one of those 3 building blocks of cognition. Anybody remember? Yes? Yep, exactly. So affordances, right? The advertisements that objects send out about how you can interact with them. What were the other 2?
Self and non-self, discrimination, and short-term memory.
Absolutely. So discriminating between self and non-self, something that humans get out of the way relatively early in our infancy, something that robots still struggle with. And as you mentioned, short-term memory, of course, very important aspect of cognition. So let's pick up where we left off. Last time, which was looking at the short-term memory. How are we evolving robots to form memories? By making them blind the moment they start moving. If you remember a few weeks back to the gantry robot, the robot could remember and move at the same time. So whatever the gantry robot was doing, it was relatively complicated. This is kind of a way to simplify things. We're forcing the robot to remember because it goes blind when it starts moving. Just as a reminder, this robot is being controlled by a CTRNN with 2 motor neurons that drive the robot left and right across the bottom of the screen, and 7 sensor neurons, or 7 sensors connected to sensor neurons, which are these 7 proximity sensors. They're reporting values corresponding to the length of these beams, but the minute the robot starts moving, all 7 sensor values are clamped to 0 for the remainder of the simulation. We saw the robot did a pretty good job at this. So we're looking at analyzing one evolved CTRNN, the best one at the end. And generally speaking, wherever the object hit on the bottom of the screen horizontally, the robot had more or less the same horizontal position on the bottom of the screen. It wasn't perfect. There were certain areas where it wasn't doing so great. We've seen this many times already. Evolution is a satisficer, not an optimizer. It produces pretty good solutions, not perfect solutions. Why is this particular robot failing? Or why is this particular evolved CTRNN failing? Here's a bit of a hint. So again, takes a minute to learn how to read these particular figures. In this case, we're dropping the object from above 1, 2, 3, 4, 5, 6, 7, 8, 16 times. We're going to drop the object 16 times from various positions at the top of the screen. And you'll notice in all cases, the trajectory is directly vertical, meaning the object is moving straight down. When these lines become diagonal, that's the robot moving. And as you can see, all of these diagonals are converging on a horizontal position of 0, meaning that the robot has a horizontal distance of 0 between itself and the object when the object gets to the bottom of the screen. So the robot is more or less catching the object in all of these cases. The black trajectories show cases where it does particularly well. You'll notice all the black lines converge at exactly 0. So those correspond to the 10 out of the 16 cases where the robot was exactly where it was supposed to be. And the remaining 6 cases in gray, the robot didn't do a perfect job. What's going on? Why do you think it's failing in those 6 cases and doing well in the other 10? Was it just accident, which often happens in natural evolution and artificial evolution? Or was there a reason for it?
Maybe they were dropped out was really close to being outside of the field of view, so maybe some of them managed to make it out before the robot too much.
Absolutely. So if you look at the 4 trajectories here, right at the top corners of the screen, and if we go back and look at the proximity sensors, it's not quite clear from this cartoon how long these beams actually are, but I think you're right. I think what's happening in these 4 cases is the object is just able to be sensed by the robot for a very brief period of time, but as the object falls, very quickly, the object falls outside of this sensory cone. The robot can no longer see it, and even if it tries to move to try and see it, it goes blind. So it's only able to see these 4 objects for a very, very brief period of time. Yeah? These 2 in the middle, who knows what's going on, right? It's probably just something that it didn't see during evolution. So as we've seen a couple times already, the robot evolves to do a relatively good job, but it's obviously limited by its sensors and motors, as we've seen before. Okay. Here's another example. This is a second experiment in the same set. In this case, they're again going to blind the robot the moment that it starts moving. But in this case, all of the objects are going to fall diagonally to the right from the top of the screen. And again, the fitness function is still the same. The robot has to be at the same horizontal position at the bottom of the screen as the object when the object gets there. And again, we see that on average, the robot is in more or less the right place when the object hits, but not perfect. Here's an example of what the best evolved CTRNN caused the robot to do when CTRNNs were evolved under diagonally falling objects. What is the robot doing in this case? How's the robot moving? Yep.
I think it's moving in like steps. If you read that correctly.
Yeah, it's kind of hard to see. So it's kind of moving towards the object and sort of jinking back and forth. It's a very technical term, jinking back and forth, right? Compared to, in this CTRNN, this evolved CTRNN, the robot stayed stationary for a certain period of time and then started moving. And you'll notice the slopes of all of these trajectories are exactly the same, meaning the robot never hurried or dawdled. It always went at exactly the same velocity. So you can kind of get a sense of the heuristic that the evolved CTRNN is embodying in this case. Wait until a certain period of time, and that time may be different depending on where the object is. And at that point in time, as long as you move at this speed, either to the left or the right, you'll be in the right place at the right time. This evolved CTRNN, evolved under diagonally falling objects, came up with a different solution. The robot also doesn't move for a while. You'll notice all of these lines are perfectly straight for a while, and then suddenly we start to get these kinked patterns, which represent the robot starting to move. So it's approaching the object by moving a little bit towards it, a little bit away, a little bit towards it, a little bit away, and a little bit towards it. Why? Kind of a trick question. There's no particular reason why it has to move one way or the other. There's nothing in the fitness function that says get there quickly. The fitness function is only penalizing for d sub I, the distance between the agent and the object when the object hits the ground. Doesn't matter how you get there, or how quickly or how slowly you get there, or when you get there, just get there. Okay. They took the same CTRNN, they wanted to test it again to see how it would generalize to objects falling at different angles. And again, you can see this CTRNN does a pretty good job. It's not perfect. Just kind of showing you the diversity of solutions that come out, generally speaking, when we're using evolutionary robotics. Doesn't always hit on the same solution. We get a diversity of solutions. All good? Okay. Let's move on to the fourth and final one. This is definitely the most fun one. In this fourth case, we're going to look at attention. This is something we haven't actually talked about before. It is an extremely important building block of intelligence, right? Hopefully, at the moment, you are selecting to attend to my voice and to the slides up here and where I'm pointing. And hopefully, you are choosing or selecting not to attend to all the other things that are going to happen in your day that you could be thinking about. We've already removed all devices from the phone, so they're not vying for your attention. Choosing what to attend to and when during your day-to-day activities is actually an extremely difficult thing to do, right? We are instrumenting our world with more and more technology, which is pulling at your attention in lots of different directions. As you've all probably experienced, it's pretty tiring, right? Very difficult to stay focused on a particular, on something of interest to you or importance to you, and to choose what that thing should be given what's currently going on. How do animals, and how might we evolve robots to selectively attend to certain stimuli in their environment that are important at that place at that time? Okay. We're going to test this again in a minimal system. So again, we've got our little Space Invaders robot moving back and forth along the bottom of the screen. So it's got 2 motor neurons, which are pushing it left and right. As always, it's got its 7 proximity sensors. So we got 7 values coming in at each time step of the simulation, reporting the length of these beams. This robot does not go blind. It can sense and move simultaneously. We're going to drop pairs of objects from the top of the screen. And as you can see by the 2 black dashed arrows, these objects can fall at different angles. You can see from the length of those vectors that they can fall at different speeds. And obviously, they can hit the bottom of the screen at different horizontal positions at different times. So things are getting a little bit more challenging now for our little Space Invaders robot here. We're going to, again, compute the performance of each CTRNN. We're going to evaluate each CTRNN num trials times. And each time we're going to subtract the sum of P sub I, all of the performances of the robot in the ith trial. And performance here is going to be the sum of the horizontal distance between the agent and the first object when the object hits the ground, and the distance, horizontal distance between the robot and the second object when the second object hits the ground. Yeah. So an ideal CTRNN will score all D's all of 0, all 2 times n, all 2 times n trials D's will be 0. The robot will always be there when any object gets to the bottom of the screen. Question?
Is there a reason that we choose to have the fitness function kind of not decrease as opposed to, I guess, increase when you get it correct?
Yep, I think this was just to make things simpler on the investigator, right? It doesn't really matter. In this case, we're just assuming that higher values are always better, and it's easier to just work with positive values instead of having to think about subtracting minus values and so on. There's probably a more elegant way to write this fitness function, but generally speaking, we're always penalizing for horizontal distance between the agent and an object when the object gets to the bottom of the screen. Yeah, okay. It's not clear from this cartoon which is object 1 and which is object 2. For the sake of our discussion today, object 1 will be the one that hits the ground first. Object 2 will be the object that hits the ground second. Okay. This work was done just when physics engines were appearing on the market, so these investigators sort of made their own little cartoon physics engine. David Buckingham, who took this course a number of years ago now, chose to tackle this for his final project, and this was his video submission for his final project. What makes this task so difficult? There's several things that make this task difficult. Yep?
The sensors don't cover the whole field?
The sensors don't cover the whole field. So you have to remember, in this case, so memory is required. Yep.
It has to choose which one to catch first.
It has to choose, right? So that's the selective part of selective attention. What does it pay attention to and what does it go after? What else makes this task difficult?
It cannot be fast enough if the object is solving rapidly.
It's possible that you can see obviously there's a maximum speed here for this robot. It can get itself into a situation where even at max speed it won't be able to get to where the object is going to hit. Yep. What else makes this task difficult? Yep.
Predict future positions of the two objects and remember.
It has to predict future positions, and we're going to put all of those in imaginary scare quotes, right? However it does that. So there are many other aspects of cognition that are hidden in this task in addition to selective attention. Prediction, I think this is the first time in this course we've talked about prediction. One of the most popular definitions or formal definitions of intelligence in the AI field is to make sure you don't get yourself trapped in a corner in the future, or in other words, keep your options open, right? So this robot has to, quote unquote, think about the future and make sure that it doesn't move in the present in a way that's going to make it impossible in the future for it to catch one or both of these objects. How it goes about doing that, you can see this particular evolved CTRNN actually does a pretty good job. How it does it, again, very hard to tell, but it's an aspect of this problem. Okay, so when we talk about this problem, we're going to talk about two subproblems that are sort of embedded in this problem. The first one is the passing objects problem, which is yet another problem with this. In this cartoon example here, at this moment in time, the object on the robot's left is closer to it, but you'll notice that it's moving more slowly. The dashed vector is shorter than the other dashed vector. So the right-hand object is actually moving faster. And in this cartoon, the idea is going to be that actually, at some point, the right-hand object is going to pass the left-hand object, meaning suddenly it's going to be closer to the robot than the one on the left. and the right-hand object is going to hit first. And in many cases, the robot is going to need to know that before this object passing event happens. Separate problem is the object permanence problem. As you saw in that video, depending on how the robot moves, intermittently, the robot will not be able to directly sense one or possibly both objects. And it has to remember where they are, where they were headed, and probably their velocity as well. Yeah? So looks simple, but this is definitely a very challenging problem. Okay. Passing objects problem and the object permanence problem. We're going to look at an evolved CTRNN at the moment. And as always in this paper, the investigators are going to play back that evolved CTRNN under several different conditions. And they're going to do so in increasingly difficult conditions. The first condition we're going to look at, there is no passing objects problem and there is no object permanence problem. That's this one up here. No passing objects problem and no object permanence problem. The second environment, the objects are going to pass one another. In the third environment, the only way to solve this problem is to move in such a way that you can no longer see one of the objects for a considerable period of time. So in this environment, the robot is going to be challenged to solve the object permanence problem, but not the passing objects problem. And in the last two environments, the robot is going to have a really hard time. It's going to have to deal with passing objects and objects that pass in and out of its field of view in a relatively easy way and then a more difficult way. Okay, let's have a look at each of these in turn. As always, these investigators were very creative with coming up with a figure that shows everything that was happening in a simulation over time to the objects and to the robot. So we've got time increasing as we move downward in this figure. So we've got the objects falling from the top of the screen towards the bottom of the screen. You'll notice that there are two straight trajectories, two straight black lines embedded in this figure. What do the two straight black lines represent?
Balls in shark tank.
It's the what about the balls does it represent?
Their trajectory.
Their trajectories, right? So you can get a sense of their direction. So the object that was on the robot's left to begin with is falling straight downward. And the object that was a little bit to the robot's right is falling down and to the right. What is the fact that one of these trajectories finishes higher than the other one? What does that mean? What does that tell you?
Means that object got to the bottom first.
Absolutely. So in this case, the left object got to the ground first, and then some significant time later, the right-hand object hit the ground. What does the jagged black line represent?
That's kind of the jinking of the robot back and forth.
The jinking of the robot, right? So the non-straight line is the movement of the robot itself. So we can see in each of these figures three different trajectories: the trajectory of both objects and the trajectory of the robot. What do the two trapezoids represent? This one's a little trickier.
The field of view.
The field of view. So let's start with the lighter trapezoid. Right up at the top where the trapezoid is wider, that means that the robot could have any of these horizontal positions at the bottom of the screen. The robot can only move left and right at the bottom of the screen. And at any of these horizontal positions, the robot can see the left object. At this point in time, when the object is just about to hit down here, where the lighter trapezoid is narrower, there is a narrower range of horizontal positions in which the robot can still see that object. If the robot was sitting over here, for example, the beams would be reaching, its cone would be reaching up here, and the object would be underneath the right-hand side of the robot's sensory cone at that point in time.
Does this robot no longer have the thing where it can only see when it's not moving?
Correct. This robot can see and move simultaneously. It never goes blind. But it can be blind to an object if that object is not in its field of view. Yeah? Make sense? So the darker trapezoid, these at any point in time, if you take a horizontal slice through the darker trapezoid, that represents horizontal positions in which the robot can see the right-hand object. So far, so good? Okay, so this one is relatively easy. There's no passing objects problem. So the left-hand object, we know, hits the ground first, then the right-hand object. Because there's no passing object problem, that means that the left object must have already been closer to the robot at the initial condition. So if we go back to the cartoon for a moment, these objects are not both dropped from the top of the screen. They're dropped at different initial vertical positions. So in this example here, the left-hand object is closer to the robot and it hits the ground first, and then the right-hand object hits the ground next. No passing objects problem. How do we know that there is no object permanence problem? You can actually see it in the figure. There's no point in which the robot needs to not see one or both object.
You can tell because the wedges are overlapping at the bottom.
Absolutely. So the trapezoids are overlapping at the bottom. At the moment that the first object hits, you can see the agent is actually right there. It catches the first object. And at that point in time, the agent's position is still inside of the darker trapezoid. It can still see the right-hand object, which is still falling. No need for not seeing any of the objects. The robot is quote-unquote watching the first object to know how to be there in the right place at the right time. And it's also always watching the right-hand object. Again, we'll put scare quotes in there. We're not exactly sure what that means by watching, but if it needs information from both objects, that information is immediately available at all times. So far, so good? Okay, same evolve C tier and N. We're going to replay it now. Now we're going to make the task a little bit more difficult. We're going to introduce the passing object problem. The object that is originally further away hits the ground first. What is telling you that in this figure? The dotted line, right? So at this point in time, the left-hand object, which was originally further away, passes the right-hand object and then hits the ground first. Compare the jagged trajectory in this figure to the jagged trajectory in this figure. What is the robot doing differently in this more difficult situation?
Trying to go between the objects, like discern which one to go for.
Right, it's trying to decide. You can see it jinking back and forth underneath both objects. It looks like it's trying to decide which one to go after. And it doesn't really seem to, quote unquote, make up its mind until just in time, right? Most of the time, it's hanging out between both objects and then drifts a little bit to the left and catches the left-hand object, and then immediately starts heading over to get underneath the right-hand object, and then the robot starts showing off a little bit and actually moves exactly, indicating that it knows exactly where the object is going to hit. You know? Okay. Well done, robot. Okay. Let's play the same evolved C tier and N a third time. Now we're going to look at the inverse environment. In this case, no passing object problem. The object that's closer is going to hit the ground first. But now we're introducing the object permanence problem. The robot, if it wants to succeed at this task, cannot keep both objects in view at all times. What does the robot do in this case? Can you see the moment in time when one of the objects passes outside of its field of view?
So like, well, it needs the first one that hits, and then it runs all the way across the screen.
Yep.
It remembers its position before it could go out.
Absolutely. So at this moment in time, when it catches the left hand, the object that was originally on the left but has now fallen, hit on the right. At this moment in time, it immediately starts motoring towards the left relatively quickly. The slope is relatively horizontal. It's moving relatively quickly. So it's hard to know what the robot knows at this point in time, but it seems to know that the other object, which it can no longer see, at this point in time, it's outside the dark trapezoid. It cannot see the dark object, or the object on the right. It knows that that object is to the left, and it probably knows that that object has actually drifted quite a long distance to the left, because it's moving quite quickly. It actually gets there with still a fair bit of time and starts showing off again by jinking back and forth and tracking the object, showing it's not only knows where the object is, but where the object is going to hit. Yep, all good? Okay, let's have a look at the second most difficult environment now. We've got the passing objects problem. So the left-hand object is originally further away, but hits the ground first. The other object is closer, but is moving slower and hits the ground later. At this moment in time, the faster moving object passes the slower moving object. And we also have the object permanence problem. What is the robot doing in this pretty challenging environment? Again, we'll put imaginary scare quotes around everything here. What is the robot thinking? What is the robot doing?
It still looks like it's trying to stay in between them.
It's trying.
Figure out which one to go for first.
Absolutely right. It's staying in between. It's staying in between right until here. This is the moment where the two trapezoids diverge. This is the moment in which it can no longer keep both objects in view. And at that moment, it makes the right decision, which is the one on the left is going to hit first, gets over there, grabs it, and again, heads in the right direction at just the right speed to capture the object that it can no longer see. The agent cannot see the remaining object until this moment in time, the moment that the black trajectory comes back inside of the dark trapezoid. There is a long period of time here, also here I suppose, long period of time in which it sees nothing. See, the other object is already hit, the other one is falling further and further to its right, and it's chasing it. Okay, same thing here, passing objects problem and the object permanence problem, but this one is more difficult. Why is it more difficult? What is it in the figure that tells you that this task is more difficult for the robot?
Because it only gets to see both of them for like a really small amount of time.
Absolutely, right? So the trapezoids stop overlapping very, very quickly. The robot is doing the right thing. It's between them and quote unquote makes a decision very quickly, which it has to do, races over to the left, slows down, shows off for a while, captures the object, and then again, it clearly, quote unquote, remembers where and when the other object is going to hit the ground and moves in exactly the right way to be there at the right place at the right time. So we have evolved a CTRNN that does a very good job at selective attention, deciding which object to pay attention to when and what to do under those conditions. And it's also dealing with some other issues. It's predicting forward in time. It's thinking about things that it can't see. This robot has a little bit of an imagination. It can imagine and remember what's happening elsewhere in its world, even though it can't directly sense those features at that particular moment in time. Pretty simple agent, controlled by a pretty simple neural network, but starting to exhibit a number of the rudiments of intelligent behavior. All good? Okay, that concludes our discussion of the first minimal cognition experiments. Any questions before we move on to lecture 10 and look at a fifth building block of intelligence? All good? Okay, so in lecture 10, we're going to look at a fifth building block of intelligence, and this one is arguably more complicated than the four that we just saw. This one is active categorical perception. Again, we'll break this term up. So categorization, this is the bread and butter of AI. If you give a state-of-the-art AI a short video clip from YouTube, it'll tell you whether there's a cute kitty cat in that video or not. It can categorize various objects that it sees. In this course, we are looking at embodied approaches to categorization, categorizing the world by reaching out and pushing against the world and observing how the world pushes back. Where have we seen an example of embodied categorization before? Babybot, right? Remember Babybot reaching out and distinguishing between self and non-self, and then moving on to learning about apples and bananas and grapes, squishable things, liftable things, pushable things. We also saw embodied categorization in the gantry robot. Didn't literally touch anything, but it categorized objects in its world. It distinguished between triangles and rectangles through movement, not actual contact, but movement, a form of embodied intelligence. This is going to be the third time that we're going to see a robot capable of embodied categorization. And it's going to do it again in this active way. It's going to reach out and influence its world. When we are performing active categorical perception, we can ask the question about how should you reach out in the world to distinguish between various objects in the world. We saw some heuristics when we saw Babybot. Generally speaking, when we interact with our world to try and distinguish friend from foe, poison from food, all the other categories that matter to us, we are generally doing so, whether we're aware of it or not, to accomplish two different goals. The first is to reduce within category differences. You've all eaten apples before, you've all held apples before. Man never eats the same apple twice. Every apple is slightly different, but when you manipulate an apple, for example, you're often doing things like bringing it up and looking at it, rotating it, holding it in a certain way, where you are reducing the difference in the sensory experience you're having with that apple to ones that you've held in the past. When you're grappling with especially mysterious objects, maybe apples aren't that mysterious, one of the things you're trying to do is manipulate it so that it becomes more familiar. Can I rotate? Can I push? Can I ask this person questions in just the right way? That I start to get responses back. I start to get sensory repercussions back from the world that say, aha, if this person is a friend, this is sort of the familiar exchange you would expect. If this is edible food and I take a bite, this is sort of the taste I would typically associate with good food compared to poisons or rotten food. We are manipulating our world to reduce within category differences for objects that belong to the same category. At the same time, we are possibly, maybe at the same time, maybe either or, we are also manipulating objects to magnify differences between categories. I think this object is not an apple, I think it's something else. If it's a non-apple, I should be able to do this and get a non-apple response. Can I magnify, if it is something different from an apple, it should act differently, it should interact with me differently. This non-apple should have different affordances if I interact with it. And if it starts to meet those expectations, my confidence grows that I am manipulating something that is not an apple. Okay, those are hypothetical examples. Let's look at a more concrete example. Imagine you have these 11 objects placed in front of you, one after the other. You take your mask and take it off your nose and mouth and you put it over your eyes. You can't see the objects anymore. I'm going to put one of these 11 objects in front of you at random, and you are going to have to distinguish between the round and the edged objects. How would you do it?
Feel for the corners.
You could feel for the corners, right? So we have a lot of tactile sensors in our fingertips not so much on the back of our hands. So most primates, including us, if they could speak, they'll say, I'll lift something up and manipulate it. There's some other simpler things you could do. If you picked it up and manipulated it, you might start to realize that this is a bit of a trick question. There aren't round and edged objects here. There are just objects with increasing edges in them, or increasingly sharp edges. If I asked you instead to manipulate these objects to distinguish between the round and the edged objects, what might you do instead of picking it up and manipulating it? Could try rolling it. So imagine you put your hand on the top of the object and then you move your hand back and forth with horizontal force. What's going to happen if you do that to these 11 objects? Let's imagine these objects are sitting on a tabletop that has relatively high friction. What's going to happen?
Only one of them's gonna roll smoothly.
Maybe only one of them. Maybe only this one will roll and the other 10 will not roll. You would conclude that that object is the round object and all the rest are edged objects. That's if we have a table with a very rough surface. Imagine if the surface is smoother and you do exactly the same thing. Now what happens?
The object just might slide.
Yeah, the objects might slide, yeah. So maybe all of them slide and now we have no distinction between them. Some of them might roll more and fewer of them might slide in this case. It depends on the surface that we're rolling. It depends on the surface of the table. It depends on how hard you're pushing down as you roll along the top of these objects. So this is meant to represent active categorical perception. You are creating categories in this case, the rollable and the non-rollable objects, by actively interacting with them. And depending on how you interact with them, that division appears at different points in this set of 11 objects. So the distinction between round and edged objects is not innate. It's not inherent in this objects. If there is a distinction between round and edged objects, it emerges from your interaction with these objects. When we train a neural network to distinguish between videos that have cats in them and those that don't, we are imposing the category. We are telling the neural network what the category is. For us embodied agents, humans and robots and animals alike, doesn't work. Categories arise based on your interactions with the world. In your social network, if I were to ask you who's friend and who's foe, you might come up with a certain subset. One of your friends who has a very similar social network, they might tag that social network with a very different distribution of friends and foes, right? Distinctions are relative to you and the way you interact with your physical world, in this example, or possibly your social world. Yeah? When you're trying to roll these objects back and forth, assuming that some roll and some don't, how is that action reducing within category differences? So within the category of rollable objects, what's happening? How is this what is this reduction? If we took the geometric difference between each neighboring pair here, the geometric difference is always constant. The object to the right is always slightly more edged than the object to the left, right? There is a constant difference between each of these 11 objects. But if we were to place our hand on top of some of them and move back and forth, suddenly maybe these 3 would roll and the others wouldn't. So the slight differences between this set of 3 would disappear. They would all start rolling. Now, depending on how much you're paying attention, you might be able to feel the geometric differences in your palm. So maybe they aren't reduced that much. But based on your interaction with these objects, you've reduced their differences. They used to be rounder, slightly more edged. Now they're just rollable, and the rest are non-rollable. Yeah? We've also magnified the between category difference. Some of these objects are going to roll underneath our hand, and others are going to slide or maybe stay stationary, depending on how we're pushing. So the difference between those that roll and those that don't, our perception of it, the way we feel those two different sets, feels very different. We're magnifying between category differences. Yeah. As always in this class, when class ends and you go about your daily routine, think about all the objects you manipulate and interact with throughout the day. I see some of you have pens here. You might use multiple pens throughout the day. They are all different pens. When you manipulate them, whether you're aware of it or not, you're reducing the within pen category differences. Okay. As always in this course, now we're going to try and evolve a robot to do ACP. This is admittedly not a minimal robot. I included this lecture in the minimal cognition series. Not really minimal, but it's still a lot simpler than us. We're going to look at this particular robot, which is an anthropomorphic robot or arm. Anthro meaning human, and pomorphic meaning kind of in the shape of. So we're dealing with not a full humanoid robot, but a humanoid arm. These investigators built in a lot of human physiological detail to this robot. You'll notice in the arm itself, there is J1, J2, J3 through J7, 7 rotational joints. You'll notice there are 2 joints in the shoulder. All of the joints inside this robot arm, they are all hinge joints, exactly the same as you've been building in your simulation. Why 2 hinge joints in the shoulder?
It like simulates like a socket.
It simulates a socket, right? So it simulates one hinge joint gives you this, one hinge joint gives you this, and if both hinge joints are moving simultaneously, if both hinge joints are rotating simultaneously, you get this. We're missing one rotational degree of freedom, right? Exactly, this one. Where is it? They actually put it in here. It's just not in the shoulder.
In the wrist?
There's 2 joints in the wrist, which again are giving you this.
It'd be in the arm, right?
It's in the arm there. It might be hard to see maybe from the back. J3 is actually embedded in the upper arm, which is actually pretty close to how your upper arm works. The 3rd rotational degree of freedom is not actually in your shoulder. If you can see my shoulder from where you're sitting, my shoulder is not actually rotating. It's my arm from about here downward. So there's quite a bit of human physiological detail in here. Whether it matters for this experiment or not, probably not, but kind of interesting to use this to bolster up your intuition of how to simulate complex objects, complex robots in a physics engine. Okay, elbow, pretty straightforward, just one hinge joint. We see 2 in the wrist, which give us this, and then number 5 in the forearm gives us this one. Yeah? Okay. There's a whole bunch of joints in the hand. You'll notice a relatively complicated hand. There are 3 joints per fingers, which correspond to the phalanges in the finger. You have a proximal, meaning the part of your finger that's closest to your palm. You have an intermediate and a distal phalange. So, and you can control all of these joints at the stem, middle, and tip of your finger. Can you control them independently? Different fingers you can control independently, definitely. How about the phalanges themselves? Most of you should be shaking your head no. Most of us cannot rotate the tip of our finger and leave the intermediate and stem of our finger as is. Hopefully most of you are playing with your hand now, right? Most of us can't, but there may be a few people here who can. There are a lot of people who can independently control some, if not all, of their phalanges. Seems like a very minor detail that will become important in a moment. Okay, so that's all the objects and joints. How are we going to evolve this robot to perform active categorical perception? We are going to, as always, evolve a population of CTRNNs. We're going to evolve CTRNNs that control all of these joints. And we're going to evaluate each CTRNN 16 times. We are going to take these 8 objects, and we're going to place each of these 8 objects under the robot's palm and place the arm in initial position A. So we're going to place the robot in position A, put the first of these 8 objects under its palm, and then allow the CTRNN to do its thing. Put the arm back to position A, put the second object underneath the robot's palm, and allow it to do its thing. On the 9th trial of the same CTRNN, we're going to place the arm at initial position B and place the first of the 8 objects underneath, allow the CTRNN to control the arm, and so on. We're evaluating each CTRNN 16 times. It has to manipulate these 8 objects, each object twice, starting from 2 different initial conditions. You can probably see what the categorization task is that we're going to evolve these CTRNNs to perform. The robot is going to have to distinguish between spheres in the top row here and then ellipsoids in the bottom row, where the ratio between the major and minor axis of the ellipsoids are pretty close to one another. It's almost a sphere, but not quite. So we're making things pretty hard on the robot. I mentioned 8 objects. They might seem like 8 different objects from the robot's point of view. From our point of view, there's obviously only 2 objects, the sphere and the ellipsoid. When we place the ellipsoid under the robot's arm, under its hand, we're going to place that ellipsoid at 4 different orientations and make sure that it can recognize ellipsoids. And then we're going to take the sphere and do the same thing. But of course, the sphere, it doesn't really matter how we rotate it horizontally. It's always the same presentation. So we're going to try and evolve a robot that's blind. It has no camera. It can't see these objects. It's going to have to feel both of these objects and tell us whether it is manipulating a sphere or an ellipsoid. So far, so good? Okay. So that's the body of the robot. Let's have a look at the brain of the robot. Let's start up here. All of the circles here represent a neuron, and you can count them all up. There's a total of 48 neurons in this CTRNN. We're going to skip back and forth from the visual representation of the CTRNN and its formal description down here. Remember that when we're dealing with CTRNNs, they are represented as sets of ordinary differential equations. If we have 48 neurons, that means we have 48 differential equations. Y sub 1 prime, y sub 2 prime, all the way through y sub 48 prime. We have tau sub i's on the left-hand side. Remember what taus do, depending on those values. And the sub I reminds us that each of the 48 neurons has its own tau value. We're going to evolve the taus in this experiment. So some of the neurons may be more or less sensitive. On the right-hand side of these 48 differential equations, the first 22 of those equations have this form. And the remaining neurons, or the remaining differential equations, have this form. Let's start with the first 22 equations, which correspond to the first 22 neurons that we see down here. We've got minus y sub I on the right-hand side, which reminds us that if a particular neuron is not stimulated, it will decay towards 0. Unless it is pushed away from 0 by uppercase I sub I, which is the sensor attached to that sensor neuron. So in this CTRNN, we have 48 neurons. 22 of them are sensor neurons. 8 of them are hidden neurons. And the remaining 17 of them are motor neurons. So far, so good? Okay. So we've got 48 differential equations, The first 22 have this form. The remaining differential equations have this form. This should look relatively familiar to you. We're summing up the weights. We're summing up the weight of influence of all of the J neurons on the ith neuron. We're adding beta here. What does beta represent? It's a slightly different notation than when we talked about C tier and Ns last time. If we're adding beta to the raw value of a neuron, what is beta representing here?
Bias.
The bias, right? So even if y sub j is 0, if beta sub j is non-zero, it can always pull that neuron's value away from 0. We've got an activation function here. Here's the particular form of this activation function. Take my word for it. This activation function will squash everything inside here to a value between 0 and 1. So far, so good? Okay. Last little detail. You'll notice that for these neurons in here, we're summing up from j equals n to m, and it gets a little confusing. For the 23rd through 30th neuron, n and m are 1 through 30. So let's go find neurons 23 through 30. We can see neurons 23 through 30 are receiving incoming synapses from the first 30 neurons, which includes all the sensor neurons plus all of the hidden neurons. So each hidden neuron receives a synapse from every sensor neuron plus every other hidden neuron, including itself. Everybody see that? Okay. For the 31st through the 48th neuron, which are the motor neurons up here, 31 through 48, they are receiving incoming synapses from the 23rd through 30th neurons, which are the hidden neurons. That's represented by these arrows here. So the sensor neurons are fully connected to the hidden neurons. The hidden neurons are fully connected to themselves, and the hidden neurons are fully connected to the motor neurons. The investigators have built in these recurrent connections here, assuming that maybe if it needs to distinguish between spheres and ellipsoids, it's going to need a little bit of memory. So far, so good? Okay. Let's look at the actual sensor neurons for a moment. The first 7 are arm proprioceptive sensors. Remember, there are 1, 2, 3, 4, 5, 6, 7 joints in the arm. For each of those 7 joints, at each point in time, those joints provide a proprioceptive sensor value, which is the current angle of that joint. This joint is flexed inwards at minus 30 degrees and flexed inwards towards my body at minus 20 degrees. So first sensor would report minus 30, second sensor would report minus 20, third one plus or minus, and so on. We have 10 tactile sensors. Doesn't say here, but those 10 tactile sensors are distributed throughout the inner surface of the hand. So the 1 through 10 here represent the 10 touch sensors that are in the hand. So we got 17 sensors so far, 7 proprioceptive sensors in the arm, 10 touch sensors in the hand, and did I get that right? And then we have an additional 5 in the hand, 18 through 22. Where are those additional 15? I see 10. I must be missing something. Okay. I'm not sure why they're distinguishing between tactile sensors. Oh, sorry, hand proprioceptive sensors. That's why. 10 tactile sensors in the hand, 10 touch sensors. And we have 5 proprioceptive sensors in the hand. Doesn't actually show you where they are in the hand. Where do you think they are? The number 5 being the very strong hint here.
Each like
like finger, the joint.
Each finger, right? So assuming that our phalanges are dependent, we can't rotate each one in independently. If you rotate one of your fingers in, generally speaking, the angles between your proximal and your intermediate and distal are about the same. So there's multiple angles in a single finger. They just kind of washed away that detail. It's the rotation inward, the amount of rotation inward by each of your 5 fingers. 0, 10, minus 10, 0, 0, 0, minus 10, minus 10, minus 10, minus 10, minus 10, and so on. So far, so good? Okay. So a lot of sensory values coming in, 22 sensor values coming in. Let's do the motor neurons now. We have 14 arm actuators, but we only have 7 arm joints. This one's a little tricky. This is a relatively subtle physiological detail. Why 14 motor neurons, but 7 joints in the arm?
Can each joint like move forwards or backwards, and therefore it counts for 2?
Absolutely. Now we could assign a single motor neuron to each joint, where positive values mean flex away from the body, extend away from the body, and negative numbers mean flex inwards towards the body. We could do that. In this case, they assign 2 motor neurons to each joint, representing agonist, and antagonistic motor muscle pairs. Bicep and tricep are an agonist-antagonistic pair. When you send commands to your bicep, your elbow does this. When you send commands to your tricep, your elbow does this. I'm sending 2 separate motor commands to 2 different muscle groups, but they are together controlling just 1 joint. So for each pair of motor neurons, they put them in there and they basically just sum the values, and that's the torque that they're going to apply to the joint. They're not actually simulating bundles of muscle in the simulator. This was very difficult to do back in 2009 because at that time most physics engines could only simulate rigid materials. Today there are now physics engines that simulate soft materials, and later in the course we're going to look at some of those physics engines. So today, if you wanted to redo this, you could attach 2 blobs of soft material that contract in volume, and each pulls on the lower arm relative to the upper arm. Inside a soft-bodied simulator, you could probably make this simulation even more, you could make this simulated robot even more anthropomorphic. They built in this physiological detail at the neural level, but not at the morphological level. Just wasn't technically possible at the time. So far, so good? Okay. And then we have sort of the opposite case. There's lots and lots of joints in the hand. There's 15 joints in the hand, 3 joints per finger, but they only have 2 hand motor neurons. What gives? Why?
Like you're going to pick something up, you're just going to close all your fingers or open all of them.
Yep, so they're going to make this simple on the robot's hand. They're going to still have this agonist-antagonistic motor neuron pair, but it is going to extend and flex the hand inward, right? So depending on the sum of these 2 values, the hand is going to open and close. So in this experiment, not only can the robot not independently control finger phalanges, it also cannot independently flex and extend fingers. It's got to be the whole hand inward and outward. Again, just kind of a minor detail. Okay, a lot of lead up to the last 2 neurons. These are not sensor neurons, not hidden neurons, not motor neurons. They are categorization neurons. Why are there 2 of them?
One for sphere, one for ellipse.
One for sphere and one for ellipse. So if we run a CTRNN on this robot, and at the end of the simulation, the 47th neuron has a higher value than the 48th neuron, we'll assume that's the robot telling us that it's in the presence of a sphere. If 48 has a greater value than 47, we'll assume that's the robot telling us that it's in the presence of an ellipsoid. We'll assign one categorization neuron for every category, which in this experiment is just 2. That is not what the investigators did. Why not? If we want to train a robot to distinguish or categorize between different objects in its environment, why don't we just assign a neuron for every category that the robot may be interested in, or that we want to train the robot to distinguish between?
Doesn't leave room for new objects.
Absolutely. So if we expose it to a new object, we're going to have to add a new neuron and retrain some or all of the parameters that describe that CTRNN. There is a long, long running debate in neuroscience about how you do this. You recognize various categories in your environment, like, for example, your maternal grandmother. Do you have a neuron somewhere in the billions and billions of neurons in your head that lights up every time you think of your maternal grandmother, every time you call her, every time you see her on Zoom, every time you receive a birthday card from her, every time a family member mentions her name? Is there a grandmother cell somewhere in your head? Maybe, maybe not. The community has gone back and forth. Maybe yes, maybe no. You can definitely, especially today with modern technology, put someone in an fMRI and have their grandmother call their cell phone. Actually, you can't take a cell phone into an fMRI, but you can get your grandmother's voice into the person in the fMRI, and sure enough, somewhere there's a neuron in there that'll be very strongly stimulated under those conditions, and when she's not calling you. But does that mean that that neuron is responsible for your maternal grandmother? Originally, the thought was yes. Then the neuroscience community went back and said that doesn't really make sense. It's not a good use of neural real estate. Remember when we looked at the small humanoid robot that was shaking the block left and right 3 times, up and down 3 times? We could have encoded each of those motor primitives in a small bundle of neurons, but if we want to train a robot to exhibit hundreds, thousands, millions of motor primitives, we're going to need millions of neuron groups. You consistently recognize things in your environment other than your maternal grandmother. Is it a good use of your neural real estate to assign one neuron to every familiar feature in your environment? Probably not, but again, neuroscience sometimes says yes, sometimes says no. The argument still goes on. First generation of neuroscientists argued about this. Second generation of neuroscientists argued about this. My generation argued about this, and they renamed it the Jennifer Aniston neuron because the evidence was weighing back in favor of this view of the brain in the 90s, I guess it was, when she was popular. I don't know what the meme is today, but again, there's some particular name for this phenomenon. It's not clear what is going on in neuroscience. In this experiment, they chose to not do this. They are not going to assign one neuron to each possible shape that the robot can see. And they did it for the reason that was mentioned up here at the front, which is, as you're going to see probably next time, you're going to see that they can retrain this neural network to recognize 3 different kinds of objects, 4 different kinds of objects, 5 different kinds of objects, with reusing the same 2 neurons. So you're going to see in this experiment how neurons are evolved for a particular purpose, distinguish between spheres and ellipsoids, and then later they can be repurposed or new functionality can be added to them. It is very non-intuitive for us to think about that different sets of neurons light up differentially when you think about your maternal grandmother. They light up differently when you think about your paternal grandmother, when you think about Jennifer Aniston, when you think about this, when you think about that. It's much less intuitive, but it has the advantage that it's an efficient use of neural real estate. We can pack more and more cognition. We can pack more and more categories into these two neurons. We got 4 minutes left, so I'm just going to start to introduce how this actually works. They are going to observe not the final value of neuron 47 and 48. They are instead going to watch how these two neurons change over time. Remember that we're not looking at the raw value of the 47th or the 48th neuron. We're going to look at the value that pops out the far end of the activation function. And this activation function always ranges between 0 and 1. So if I create a two-dimensional figure where we're going to put the value of the 47th neuron on the horizontal axis, and we're going to put the value of the 48th neuron on the vertical axis, and these values are always going to range between 0 and 1. We can then plot how these two neurons change over time as a trajectory moving through this two-dimensional space. I don't know what the initial values of neuron 47 and 48 are, but let's assume the initial values of 47 and 48 are this. The robot is starting with its palm on the object. It starts moving. When it moves, it changes its sensor values, which change the sensor neurons, which change the hidden neurons, which change the two values of neuron 47 and 48 at time step t1. This was the value of these neurons at t0. At the next time step in the simulation, they have a new value. And then at the next time step, another value, pair of values, another pair of values, another pair of values. And at the end of the simulation, at time step uppercase t, t sub uppercase t, we've got the end of this trajectory. What we have just done is to draw the trajectory of this value pairs in a phase diagram. If you ever take a dynamical systems course in the math department here, you will see phase diagrams. They are a very handy tool because they allow you to visually represent not just how one variable is changing over time, but how multiple variables are changing over time and how they are changing values relative to one another. So far, so good? Okay. I think this is probably a good place to pause for today. You have a quiz due tonight. You're working on assignment 6, where you're incorporating neurons into your simulator robot. See you on Thursday.